Due to the great importance attached to the environmental protection worldwide, the technology and application of lithium batteries have developed rapidly in recent years. However, both in the fields of new energy vehicle and energy storage, the fire hazard caused by battery thermal runaway has always been a surmountable problem. The gases produced by thermal runaway consist of hydrogen, carbon monoxide, hydrocarbons, and electrolyte vapor, which are highly combustible. It is extremely dangerous if these gases spread into the air and form explosive mixture. At present, lithium battery thermal runaway events have occurred repeatedly in countries around the world. In the morning of July 30th, 2021, Tesla's lithium battery energy storage project in Australia caught on fire and was burning for 5 days, but fortunately there was no human casualties. In the morning of April 16, 2021, the Leafy Pure 4 energy storage project at Dahongmen, Beijing misfired and exploded, resulting in the death of 2 firefighters and 1 other personnel. The aforesaid are just 2 typical cases from last year, and there are a great number of accidents every year, so the safety of lithium battery energy storage systems has always been a pain spot for the industry and needs to be addressed urgently. The current measures in the lithium battery storage station is to equip clean gas fire extinguishing agent in the container. When thermal runaway occurs in one of the batteries, the extinguishing agent erupts, cooling down the equipment and putting out the flames. The commonly used gas fire extinguishing agents include perfluorocarbon, heptafluoropropane, aerosols, water mist, etc. Those extinguishing agents are normally used in large computer rooms and other electrical premises, featuring low fire extinguishing capacity, no residue, and less damage to electrical equipment. The battery catching fire is in fact a gas fire, similar to the liquefied gas fire, featuring that explosion count before combustion. Therefore, using clean gas extinguishing agent to put out lithium battery fire is not correct.
Thermal runaway test of a 280R battery cell experimental standard. This experiment follows the Chinese national standard 3627622023 lithium-ion battery for electric energy storage thermal runaway standard. Purpose of the experiment: charge a single 280R lithium-ion battery in a fully charged state using a 6Q60V100A power supply continuous charging until the battery triggered thermal runaway. During the experiment, observe and record the smoke release when the battery thermal runaway cut-off condition. When the experimented battery voltage drops below 1 V or close to 0 V, end the experiment. Sino-Australia Energy Storage is the inventor of the world's first cell-level submerged active fire protection system, which is automatically activated in the event of thermal runaway by a self-developed fire protection monitoring system built into the battery case. When the battery vent is opened, the electrolyte and smoke enter the fire-sharing airway through the battery cover. The system quickly cools down and liquefies the gases electrolyte emitted from the battery and adsorbs and filters the recycling process to ensure that the smoke emission is orderly and controllable and does not leak out, thus completely solving the problem of the explosion and fire risk of the thermal runaway of the lithium iron phosphate battery. We pioneered a four-dimensional active fire monitoring system for detecting and responding to battery thermal runaway. The system determines the gas composition in the battery box in real time by building a TVOC monitoring probe into the shared gas path inside the battery box. When the battery is deflated, the TVOC monitoring probe will immediately detect the gas composition and synchronize the monitoring of gas inflow and discharge of the second battery box. Trigger the TVOC alarm at the same time the gas flow of the deflated fumes triggers the gas flow meter on the pipeline, further confirming the thermal runaway of the battery deflated state. To ensure that the system responds to deal with in a timely manner, more advanced is that the pressure sensor on the main water back to the gas in the pipeline will also be synchronized pressure detection for the battery thermal runaway state to provide a composite basis for judgment. After the system confirms the thermal runaway, the temperature control fire module will automatically open the water inlet side of the thermal runaway battery box normally closed solenoid valve, and at the same time close the pipeline solenoid valve of the unaffected battery box. The inlet and outlet pumps start to work, injecting the firefighting solution into the battery box where thermal runaway occurs, and carrying out cooling, liquefaction, adsorption, filtration and recycling of the erupted electrolyte fumes, so that the fumes do not leak out and there is no risk of explosion and fire. In order to ensure the long-term monitoring of the system to ensure effective operation when triggered, we also built in liquid level sensors in the firefighting water tank. When the firefighting solution is insufficient, we'll immediately send a message to remind, to ensure that the system is always in the best safety monitoring state. Thermal runaway test of a 280Ah battery cell, experimental standard. This experiment follows the Chinese national standard 36272023 lithium-ion battery for electric energy storage thermal runaway standard. Purpose of the experiment: charge a single 280Ah lithium-ion battery in a fully charged state, using a 6Q60V100A power supply continuous charging, until the battery triggered thermal runaway. During the experiment, observe and record the smoke release when the battery thermal runaway cut-off condition. When the experimented battery voltage drops below 1 V or close to 0 V, end the experiment. When the first leakage of the core has occurred, the TVOC sensor in the box has detected harmful gases, and the gas flow valve value has changed significantly. Currently, the temperature of the pole column of the core is 57 摄氏度 and 58 摄氏度. The surface temperature of the core is 57 摄氏度, and the voltage is 4.8 V. Since the core has had the first deflagration, the firefighting system is automatically activated, and the water valve on the left side is opened, and the self-developed firefighting solution rapidly enters the upper cover of the box to cool down and liquefy the thermal runaway core. When the battery cell voltage reaches a maximum of 20 volts, the battery pole temperature of 94 degrees to 96 degrees, the battery cell surface temperature reaches 100 degrees. At this time, the battery cell internal diaphragm failure, positive and negative plates are completely short-circuited. the battery experienced a second leakage explosion. During the experiment, the battery cell voltage dropped rapidly. A large number of electrolytes sprayed out and discharged with the fire system cycle, the whole process without smoke leakage. At the end of the NPS first active firefighting system experiment, we opened the adsorption tanks and found that both the adsorption tanks and the firefighting tanks were filled with lithium salts and organic compounds that had been cooled down and liquefied, which were converted from the gaseous electrolyte that had been ejected from the batteries. NPS is world's first active fire protection system, and four-dimensional active fire monitoring system at the cell level have been verified by several rounds of rigorous battery thermal runaway experiments, and the system has been successfully activated, with no leakage of smoke to completely solve the risk of explosion and fire caused by thermal runaway of the FEPO batteries. This innovative technology not only greatly improves the safety and reliability of the system, but also establishes a new safety and fire monitoring standard for the energy storage industry and promotes the sustainable development of the electrochemical energy storage industry.